In the last part of this lecture, we will talk about training of these multi-layered neural networks. So far, we've simply constructed the mapping, and we know what the parameters are. So now, how do we train it? How do we learn the parameters? First thing we want to study is the three sets: training, validation, and test. So whenever we actually embark on creating a new machine learning algorithm, or new deep learning algorithm for computer vision, we really need three different tests. The first one is a training set, where we will use it to determine the best model parameters. The second one is the validation set, and we've already talked a little bit about it when we talk about choosing the architecture of the network. The more abstractly, the validation set is used to determine the hyperparameters of a system. And we'll talk a little bit about this now. And the last set is the test set, which is explicitly used for estimating generalization accuracy. So let's talk about the training set first. In the training set, what we have is we have the features and the corresponding labels. And our goal is to find the model parameters that minimize the cost function for the training images. So we've seen this cost function before. We have the model prediction, the ground truth labels, and discrepancy, that the function that quantifies discrepancy, and we will simply find the algorithm parameters that minimizes this cost function. And the role of the training set is to allow this optimization. Now, the size of the training set is quite important, especially when we have larger number of training examples. We can fit models with larger number of parameters. If we only have very small training sets, then the complexity of the models that we can fit is also limited. The second set is what's called the validation set. In a validation set, I always also have the features and the corresponding labels. And the role of the validation set is to fit the hyperparameters. And these hyperparameters can be, for example, the architecture, so the number of layers, the width of the layers, the type of the nonlinearities, the number of iterations that we use to train the model, using or not using regularization coefficients, how to set them, or even the batch size, we will see in a second how to set it. So there are quite a number of hyperparameters of a deep learning model, or in general machine learning models, and the goal is to be able to set it. So how do we do it? Ideally, we want a validation set that has no overlap with the training set. So what do? Is we choose a certain set of hyperparameters. So we try a certain architecture, and we train it until certain training iterations. And we train this model, this specified model, with the training set, and then we evaluate how well it performs on the validation set. And we basically choose the hyperparameters that achieves the best validation set error. Now, the role of the validation is determining the hyperparameters. Notice that although we evaluate how well our model performs, the score that we obtain, the performance that we obtain on the validation set is actually not the real performance of the model. For that, we have the test set. And its only role is to estimate the model prediction accuracy. And there should be absolutely no overlap between the test set and the others, training or validation. Once we train the model, once we find the best hyperparameters with the validation set, we fix the model, and we only evaluate the model on the test set and find the discrepancy between the model predictions and the ground truth labels. The model parameters or the hyperparameters should not be changed based on the test accuracy. If you do that, you already included the test set in your validation accuracy. And this is crucial for finding the performance, the real generalization accuracy for a given neural network. Ideally, the test set should come from the same distribution as the validation set. For example, if I'm interested in creating a autonomous vehicle, I should basically train the algorithms that runs this vehicle by showing them lots of examples of images that are taken from both day and night, for instance. So if I want to now compute the generalization accuracy of the model in this vehicle, I should use similar set of images, different but similar, coming from again day and night, to find how well it performs. Now the variations in the distributions can reduce the prediction accuracy, and that's what's called the domain shift problem. For instance, if I train a model in Sweden, where there's quite a bit of snow and the weather is, in a certain sense, a little bit different. If I train an autonomous vehicle to drive in Sweden, when I now try to transport it to, for example, Kenya, I might have some troubles because the weather in Kenya might be very different than the one in Sweden. The road conditions in Kenya would be very different than the ones in Sweden. So these variations have to be taken into account. If I want to, for example, create a vehicle that can perform well on both Sweden and Kenya, then I really need to train it with images from both of these countries, in the ideal case. So some notes: generalization accuracy computed on the test set will often be lower than the one on training set. And that's normal because on the training set, I basically tune the parameters to get the best accuracy. So they will give you an optimistic picture of the real generalization accuracy. If you want the real value, then you only look at the test set. Too much difference between the test and the training accuracy points out to actually what's called overfitting. So your model fits to noise in the training set, and it's not fitting to the real pattern that gives you the ability to predict the labels. These noise patterns are actually by chance correlate to the labels in the training set. And if you have a very complex model, then it will basically fit to it. For small data sets, it's difficult to basically separate it into three different components. So one actually uses approximations like the cross-validation and the bootstrap sampling and jackknife resampling. Now, these are not as good as using a separate test set or a separate validation set, but if you have very small number of data sets, which is kind of the case in some medical applications and biological applications, then one can actually also use cross-validation, bootstrap sampling, and jackknifing to compute the generalization accuracy or approximate the generalization accuracy. Next, we will briefly again talk about the cost functions. We'll see them before, but we said that the cost functions are quite important and it really depends on the task. It's extremely important to choose an appropriate cost function. Usually it sums over all the training samples, assume that the training samples are independent, and we've already seen the binary classification cost function, the cross-entropy, and for the multi-label classification cost function, the multi-label cross-entropy. We've seen these things. When we're solving regression tasks, we can actually solve the L2 loss or the L1 loss, and we can basically minimize each of them. And I think we've already seen these quite a bit, but the most important thing is the cost function is chosen according to the needs of the model. So it really depends on what you want to solve. If you are solving a regression task, then you should use a regression cost function. If you're solving a very complex task, you should basically create a cost function as much as possible that evaluates the final output. Okay, now we will talk about the backpropagation. So this is the core technology that allows us to train multi-layered neural networks in a reasonable amount of time. So before doing that, let's show a small video about the concept here. So the backpropagation algorithm starts with a neural network and a certain set of samples. So for example, the input, I have an image, and the input to that image, well, there is a corresponding label, right? I have an image of a car, for instance, and desired output is the label of a car. So I already have a neural network. Somehow I initialize the weights, and I simply feed the image through the neural network. So I have different weights that goes from the first layer to the second, and so on and so forth until the end. Now, my ground truth for this sample says that it should be a car. The prediction, however, might be different, especially at the very beginning. So, for example, with these weights, my algorithm might predict that this is actually a plane. What I do is I compute the error at the end, and I simply try to fit the prediction to the ground truth by updating the weights so that my prediction fits the ground truth. So how does it exactly work? It's actually a very simple application of the chain rule. So whether classification or regression, our goal is that we want to minimize a certain cost function. We have the weights and the biases of the network, and we will tune them. Now, even the simplest networks may actually lead to quite complicated optimization surfaces, and most likely these optimization problems are non-convex. Sorry, I lost my mouse again. Non-convex. So in this scenario, we cannot really use complicated but successful optimization algorithms. And one that actually is being quite often used is the simplest thing, so gradient ascent, so gradient-based optimization. And in its simplest form is as simple as this guy here. So this is the steps of the optimization process. So I have the parameters at my time step t. Now I compute the derivative of the loss function with respect to that parameter and simply add its negative to the parameters, doing gradient descent. Now I have my parameters in the next step in the optimization, in step t plus 1. And I repeat the same thing again, taking the derivative of the cost function at that new value and simply repeating it multiple times. Now the critical part here is how do I actually compute these derivatives? Notice that the neural networks are basically a composition of multiple functions. So the output f in a multi-layered neural network is simply multiple functions composed one after the other. So how do I actually find the gradients of a certain weight at a given layer? For example, I'm looking at layer L, or the transition between layer L minus 1 to L, and I want to find the derivative with respect to a certain weight value in this matrix or a certain bias here. How do I find it? Now, I simply use gradient rules. So we will focus on a certain weight or bias, and we will simply compute the partial derivatives simply as given like this. So the partial derivative of the weight with respect of the cost with respect to the weight is simply given by the partial derivative of the cost with respect to the function, so the output of that layer, and multiplied by the derivative of the function value with respect to the activation, and the derivative of the activation with respect to the weight value. And it's the same thing for the bias. But notice that L is defined in terms of F. F is basically at the end of the neural network. So that's the output of the last layer. While here, I simply compute the derivative of L, the loss, with respect to the neural network, the layer values at another layer, L. So how do I do it? That's where the chain rule kicks in. So again, we have three components here. Two of them are quite easy to compute. The first one, so the derivative of the function value, the output of my layer with respect to the activation, is simply the derivative of the nonlinear function. Now the derivative of the activation with respect to the bias is simply 1. That's very easy. The derivative of the activation with respect to a certain weight function is simply the value of the hidden layer at a certain component in the previous layer. But then how do I actually compute this guy here? For that, let me define an error signal. Now the error signal will be actually the combination of these two components here. So the derivative of the loss with respect to the layer value and the derivative of the layer value with respect to its activation. Right? So the derivative of loss with respect to the activations, a certain activation in that layer. Now the gradients with respect to the error signal, or the gradients with respect to the weights and the gradient with respect to the cost, can be actually written in the form of the error signal. So I simply multiply the error signal with the activation in the previous layer to get the derivative with respect to a weight, and simply feed in the activation, the error signal itself, if I'm interested in the derivative with respect to the bias. Now, the bottom line is the chain rule works as the error signal is propagating backwards. Let's look at the error signal at layer L for a component in that layer, the ith component. Now, this, again, requires the computation of the cost function and its derivative with respect to the layer, the ith component in layer L, and that actually can be written with another chain rule based on the derivatives of the cost function with respect to the layer values in a higher level, so L plus 1. And notice something that's interesting here. Actually, all these components are very similar to what we had before. Specifically, now this is basically simply the derivative of the activation to the layer values in the layer L which is given by the weight vector, so that's quite easy. And this guy here, notice that this is actually, again, the error signal, but not at L, I, but it's the L plus 1, comma K. So it's actually the error signal in the L plus 1 layer. What this means is I can simply compute the error signal here simply using the error signals in a preceding layer. So the error signal at layer L is actually a function of the error signal and the weights of layer L plus 1. And this observation gives rise to the algorithm called backpropagation, which is simply the implementation of the chain rule algorithmically. So we start at the very final layer L, and we compute the error signal and all the necessary gradients of the weights and the biases at that layer. Then we simply propagate errors backwards and compute gradients as we do so. At a given layer L, I simply take the error signal at layer L plus 1, compute the necessary gradients and the error signal, and simply compute the error signal at layer L minus 1, and then L minus 2, and then L minus 3, until I go to the layer 0, which is simply the input. Now you can write this entire formulation in a simpler matrix notation, where I simply have the error signals at layer L plus 1 multiplied by the weight vector of weight matrix of L plus 1, and then a diagonal matrix that simply computes the derivative of the nonlinear function. Now, it's something interesting because when we talked about the prediction, we said that we basically feed in the input and flow it through the network to get the output. But when we talk about training network or computing the gradients of a loss with respect to any of the parameters, we actually did the inverse. We basically started from the output, layer L, and simply flow the information backwards. So actually, in a feed-forward network, the prediction flows the information forwards, and training flows the information backwards. The information that's flown backwards is simply the error at the output. Okay, so now we know how to compute the gradient of the final cost function with respect to a certain parameter in a network. So how do we actually implement optimization? A very simple naive approach is simply the direct optimization. So when I'm updating each of the parameters, I simply compute the gradient with respect to the total loss, meaning that I simply go over all the training examples, compute the gradients, sum them over, and add that or the negative of that to my current estimate of the parameters. But each forward and backward pass requires for me to actually fly the sample through the network once and then backwards. Now, if I actually have multiple samples, if I have actually thousands of images in my database, this operation can take quite long and it will be very, very slow. Instead, what's quite often used is what's called stochastic gradient descent. So instead, at every step, a random batch of training samples are chosen, and the parameters are updated according to only those randomly sampled samples. So what does this mean is I simply choose a subset of the entire training set at each iteration, compute the gradient with respect to parameters only for this batch, so really approximate this gradient that actually is computed for all the training samples with the gradient that's computed only for the samples in that batch, and update my parameters with that gradient. That's it. That's stochastic gradient descent. And this becomes much, much faster. And even theoretically, stochastic gradient descent leads to regularization. This I will not go into it, but if you're interested in it, I strongly suggest you to look into it. So some notes on the optimization techniques. What we didn't talk about, it was the learning rate here. So the learning rate is this guy here, which tells me how much of the gradient should I add to the current parameters. Now, learning rate is actually quite crucial. It shouldn't be too high, it shouldn't be too low. It's often set by really empirical tests on the validation set. There are many variations that are present currently for the basic stochastic gradient descent. Most of them use, again, stochastic gradient descent with additions of momentum and approximating second-order gradients. So the basic idea is, instead of taking the gradient directly, you would actually use the gradient in the previous step as well. And it's what's called the momentum. So if you're going in a direction, you want to keep going in the same direction. Different algorithms have different convergence properties. Usually the algorithm that's called ADAM, which implements a slightly different variations of this momentum, works well out of the box with minimal parameter tuning. Same thing with the RMS prop. Stochastic gradient descent, on the other hand, the simplest version without momentum, can lead to better results with a lot of tuning. And that was a very recent result that was published in the NeurIPS conference. Okay, so now we know how to compute the gradients, we know how to update the parameters. The only thing that's really needed is, how do we actually initialize the parameters? Because we have to start from somewhere, right? Well, all these gradient steps assumes that there is a theta I at 0 at the beginning. I start with that, and then I basically start taking the gradients and walking towards the gradient descent direction. So the optimization needs to start from somewhere. How do I actually initialize weights? How do I initialize the bias? It turns out that this initialization, although it looks very simple and unimportant, turns out to be quite important. If I initialize everything with 0, so weights are 0, the bias are 0, I basically create a symmetry in the system. So initialization with constant weight creates a complete symmetry. That basically means that no matter what the input value is, all the hidden units will evolve to be exactly the same value. That means all the weights will exactly get the same updates. Effectively, I will create a network with only one neuron thick. So each of my layers would only be one neuron. So that's quite bad. Initialization of the bias, on the other hand, that's often set to 0. That's commonly used, and that doesn't cause the same symmetry problem. Okay, so instead of initialization with 0, what is done right now is you initialize the weights simply with random values. So random values for the weights and 0 for the biases. And once you put the random values, then you're not symmetric anymore, because every time the input flies through the network, you will basically get a very different input, a very different output in the hidden layers. So that means that different weights will get different updates, and what's often quite used is you use random samples from either uniform or normal distribution. So there are now some heuristics to define this randomness, because the random initialization, although it's a common approach, it's unclear what distribution one can use. So the normal and the uniform are the obvious choices, but with what standard deviation of the range? So some heuristics basically say that the input to a layer, the variance of an input should basically remain the same at the output. So there are some heuristics that says you should basically sample the weights from a uniform distribution with a certain range that depends on the size of the previous layer, the width of the previous layer, or a combination of the width and previous layer and the width of the other layer, and basically lots of variations over these. The very last thing, I see due to time, I will skip to avoid the overfitting part, but I want to say that there's quite a bit of tools that are available. Python is probably currently the dominant programming languages for deep learning and computer vision. There are quite a number of libraries, TensorFlow and PyTorch, and I believe you're going to use PyTorch in the exercises. And also there's quite a number of tools for MATLAB that exists. And I think it's quite an exciting area to work on neural networks and computer vision, and there's quite a bit of resources that are available for you to quickly start playing with it and create algorithms that really can do quite complex tasks. I want to finish this with a video that I think it's kind of provides the intuition of why neural networks or deep learning is somehow reference or somehow analogies between deep learning and the human brain are made. Let's see if this actually video works. So the main idea is neural networks are the intuition for neural networks comes from the human brain. So in the human brain, the brain is composed of neurons, and these neurons are densely connected with each other. Neurons are connected with synapses, so an activation through a neuron basically flies through the axon of the neuron, comes to the synapse, and then chemically information is transmitted to the other neuron. So information flies from basically one neuron to the other neuron. And schematically, there's a dense connection between the neurons in the human brain, and it's this communication that actually allows you to do things. And the intuition and neural networks are very similar as well. So basically, we have these simple neurons, simple nodes, that actually are able to transmit information in a sense. So those are the activations, and they're connected to each other to basically mimic how the human brain works. But of course, the analogy kind of stops here. It's only kind of mimicking, because actually the human brain is quite complicated with lots of feed forward and feed backward mechanisms. While in the current neural networks, we're basically doing very simple things. But there's quite a bit of research on basically creating neural networks that are even more like the human brain and able to perform tasks with that concept implemented.